Welcome to the Astrophys podcasts. My name is Brendan O'Brien and we'd like to acknowledge Australia's first astronomers, the Aboriginal and Torres Strait Islander people, the traditional owners and custodians of the land we are on. This episode is produced on Yorta Yorta and Pangarang country in the east and Wajik Noongar country in Perth. And we're also asking you to influence your local politicians with a message that we really need to change our energy policies and move to renewable energy sources to mitigate the effects of climate change. Each month, we love bringing you two fabulous episodes. On the first of each month, our friend, molecular pharmacologist, toxicologist, and amateur astronomer, Dr. Ian Astroblog Musgrave, brings you his monthly sky guide with all the essential observational highlights for telescopers, astrophotographers, and naked eye observers. Then, later each month, we bring you an exclusive and in-depth interview with a noted astrophysicist, astronomer, particle physicist, radio telescope engineer, data scientist, or space scientist. And we discover their science journey and rare insights into how they think, when they think best, and how they conduct their amazing research into exactly how our universe works. Our audio files and transcripts are available on our website at astrophys.com. And our MP3 files can be freely streamed or downloaded to your favourite device from our SoundCloud channel, our free Audible stream, YouTube podcasts and Apple podcasts. Well, we are kicking off the year with a very special interview for you. We've been lucky enough to engage a solar physicist from Ireland who will untangle the filaments of solar flares and coronal mass ejections that our closest star bombards us with. You will love the clarity of the science that this brilliant researcher brings to the microphone. You will love Dr. Laura Hayes, and I can't wait to skip over 11 time zones to introduce her to you. Let's go. Hello, Laura.
Hi, Brendan. How are you?
Very well, thanks, Laura. Now, today, listeners, I'm really excited to be zooming over to Ireland to speak with a wonderful astrophysicist, Dr. Laura Hayes, who is an assistant professor and Royal Society Research Ireland University Research Fellow at the Dublin Institute for Advanced Studies at their School of Cosmic Physics. What a great place to work. She's doing fantastic work using the very latest instruments like the ESA NASA Solar Orbiter Observatory to unlock the secrets of our home star and to understand how and why Sol keeps hurling massive plasma packs and deadly radiation at us, grounding all those Airbus 320 planes, making beautiful auroras. I think we had a prediction we might be getting one tonight. So after this interview, I'll certainly be going out and seeing if I can see any. And another question she's working on is, why is our host star's outer atmosphere staggeringly hotter than the solar surface, despite being further away from the obvious source of the sun's heat? And this is a puzzle that has troubled physicists for about 65 years. So welcome, Laura, and thanks for speaking with us today.
Thanks for having me, Brendan, and thank you for that introduction. I'm very excited to talk about my favourite star, our closest sun.
Okay, thanks. Now, before we talk about your latest solar flare research, can you tell us where you grew up, please, Laura? And could you tell us how you first became interested in science and space?
Yeah, absolutely. So I grew up in Ireland in a seaside town called Bray. And it's always funny, I think, sometimes when, I'm a solar physicist and I grew up in a place where we rarely get to see the sun. I'm currently looking at the window and it's completely overcast. The sun rarely shows its face in the winter or in the summer, I guess at that stage. But I think thinking about why I first became interested in science and space, I didn't necessarily grow up thinking I wanted to be an astrophysicist. I don't think I necessarily even knew you could be an astrophysicist in Ireland. But I think I always loved puzzles. I always loved solving things, and I was always interested in science and maths from a young age at school. And I think I just continued with that kind of curiosity. I think really that drove me into becoming a scientist that I am today. So I guess growing up in Ireland in the 90s, didn't necessarily know of any scientists or in Ireland or whether there was research happening. Now, of course, there was, but I think my young self didn't really realize that. And yeah, so that's kind of how I started into the science world, was just general curiosity.
Fantastic, very cool. So, can you tell us a little? You mentioned school. Can you tell us a little about those school days and perhaps your earliest ambitions and if your earlier ambitions changed and evolved over time?
Yeah, absolutely. So I think going back to my school days, as I mentioned, my favorite subjects in school were science and maths. And in Ireland, when you're around 15, you choose kind of a few subjects that you would continue to do as kind of a final year exam. And it was those physics and maths subjects that I really just loved. And again, not thinking even having an ambition of becoming a scientist was not even something that I really thought about. I just really loved those subjects and knew I was passionate about them. And I think how that's changed over time, I finished secondary school to go into college and in the depths of the recession in 2009, 2010, and the job prospects weren't very great. So I thought, you know what, I'll just go to college and do what I love, right? So this is how I ended up doing physics and theoretical physics in college and kind of continued with that. I think my eyes were open then to different career possibilities that came with that. And even from university, I think doing my PhD to a few years ago to even now, my career ambitions have changed and evolved over time to seeing what's possible and what's out there. I don't think I would have thought starting college and doing physics that I would be an astrophysicist today. Absolutely not. But it's amazing to see that when you kind of open your eyes to different possibilities that a science degree allows, you kind of there are endless possibilities, and delighted that I ended up kind of working in research as I did.
Fantastic, thank you. Well, to sum up, after your successful school career, you studied theoretical physics at the famous Trinity College Dublin for your undergrad degree. Now, I'll diverge. I've been to Trinity College not as a student, but to have a look at the Book of Kells. Still, I remember the atmosphere at Trinity College is just beautiful. Anyway, then you stayed on at Trinity to complete your PhD in physics, and now you're a research fellow at the Dublin Institute of Advanced Studies. Now, for our students and early career researchers listening, could you tell us how you arranged that move to your PhD and why you decided to do your PhD?
Yeah, absolutely. So I think, looking back now, if you looked at my career trajectory, it seemed like I had a grand plan, right, of what I meant to do and where I ended up. And that necessarily wasn't the case. I think, as you say, Trinity has an amazing atmosphere, and I really loved my undergraduate degree. And it really gave me a taste of doing physics research. So it was during my time as my undergraduate student that I got to do some internships. And one of them was working in solar physics research. And I realized it was something that I would love to do. And this is where I kind of opened the door of maybe doing a PhD in physics, and the opportunity arose in Trinity. And to be honest, some part of that was I didn't want to leave college, right? I really loved my undergraduate degree. I loved Trinity. I loved that whole lifestyle. So that was one of the driving factors for doing a PhD, was like, wow, I can stay in college and actually get some funding to do some research. This is amazing. Um, and then I kind of did several years of a postdoc after that. I moved to the US, and then I moved to the Netherlands, and now I'm back in Dublin. And I think for any students or early careers listening, you can make a plan. I think I had a plan to go get a job and make loads of money and do all these things. But your plans will change. And I think if you always just end up doing something that you really enjoy and that you're passionate about, you're always going to succeed in it, right? I think if you have to be somewhat flexible to this and flexible to the opportunities. And on paper, it might seem like I had this grand plan, all these things lined up, but there was, of course, failures in there and paths that I had planned to go on and didn't work out, but kind of being flexible or changing your decisions or things like this is really important as well. So I think if you are a student or an early career researcher and you're interested in doing research and it's something that you're passionate about, I would definitely would tell you to go for that and be open to different opportunities that are out there. It might not seem like the best idea at the time, but it might work out. I think that's the biggest kind of advice is that things generally do work out if you follow what you kind of want to do.
Beautiful advice. Thank you, Laura. Now, on that track, we know how important it is to have supportive supervisors and mentors through that study and research phase. Would you like to tell us about some of the people who supported you as a scientist or as a past PhD researcher, or perhaps some of your colleagues who you're working with now who you find inspiring?
Yeah, absolutely. And I think that's a really important point, Brendan. Doing research is challenging and doing a PhD is hard, not just, doing the physics, but actually like getting through it as psychologically and kind of being interested in your research and having supportive mentors and supervisors are really important. I don't think I would be here today without a huge range of colleagues that I've been lucky to work with. So I think, the list is really endless. My own PhD supervisor, Peter Gallagher, who I currently still work with, mentored me during my PhD. He still is quite an inspiring mentor and supportive in a way of opening opportunities and getting you in touch with people and working with data. At the time I did my PhD in Trinity, there was, we had, I think, 10 PhDs all sitting in an office together doing astrophysics and solar physics research. And I think even just peer mentors was really important for me to have that kind of camaraderie during a PhD because research is really a roller coaster, right? The highs are high, but the lows are really low. So having kind of a whole kind of community of PhD researchers that were working on a similar thing at the time was really important. When I think now, solar physics in particular as a scientific research area is really collaborative. It's a really supportive environment. Incredibly lucky to work with the Solar Orbiter community. So this is a community of scientists working in Solar Orbiter all across the world, mainly in Europe and the US. And another community is the SunPy community. So SunPy is an open source software project basically for working with solar physics data. And we have kind of a community of scientists that have kind of come together to write this open source, open developed software. And there's been a few times where I've, really thought about leaving research, getting a different type of job, but it's been that community aspect of mentors within those communities that have really kept me to stay, being part of something. And I think good mentors makes the science feel possible. So again, going back to this idea of advice, I think if one of the key things for doing a PhD or research is having a good supervisor or mentor or somebody you can call on when you're a little bit lost in your research or in what you're kind of doing in your career path.
Fantastic. Thank you. And it sounds like it's a real extension of that old saying, it takes a village. Anyway, Laura, the plan for today is to focus on your solar research and have a look at the causes of solar flares, look at some of the things that the sun flings at us that cause auroras and obliterate satellites. The list goes on. And perhaps we may even have time to look at how you co-discovered the impact on our planet of the brightest object of all time, affectionately known as the boat, a gamma ray burst from 2 billion light years away in another galaxy that blasted into Earth's atmosphere and messed up our ionosphere. Who needs to watch horror movies when you study solar physics, Laura? But we will keep the focus on your solar physics research today. How does that sound as a plan?
Sounds great. I mean, talking about solar flares, CMEs, and ionospheric disturbances, it's basically a Friday night for me.
Fantastic. Okay. Oh, wow. Now, could we start with the big picture before we zoom in? What big questions are you asking about solar flares, and what problems are you working on now that you have to overcome?
Yeah, absolutely. Right. So a solar flares, there's some really big open questions we really don't understand about the sun, which is kind of funny because it's our most observed astronomical object. We've been studying it for many years. But in particular, looking at solar flares, some of the big questions I'm trying to answer are how is the magnetic energy stored in the solar atmosphere and how is it suddenly released to actually produce a solar flare, which we'll talk a little bit about in a minute. Another big question is how does this energy how is it converted to accelerate particles to such huge energy in seconds? And this is not just a problem in solar flares in our own sun, it's an astrophysical problem. How do we have acceleration of charged particles in a magnetized plasma? It's one of the key astrophysical open questions that we're trying to answer. And the sun gives us kind of a key window into doing that. Then we also want to think about, from a space weather perspective, why do some flares trigger a coronal mass ejection and why do some others not? And how can we really forecast solar flares? How can we say when it's going to happen? If you think of a space weather forecast, a storm is coming, how can we improve that forecast from looking at the sun? We're still not yet in a position to really accurately do that. And what is the physics underlying that will help us to understand and building those forecasts? And I guess the final thing is we think about when we look at solar flares in solar physics research, usually we're thinking of the largest solar flares because these cause the space weather impacts. But going back to what you mentioned about the sun's atmosphere being really, really hot, are big flares the same physics when you go down to smaller and smaller scales? And what are the small scale processes down to tens of kilometers that actually drive all this? And can tiny, tiny flares actually contribute to heating the solar atmosphere? So these are some of the big questions I'm trying to answer in solar physics. And what are we're trying to work on to overcome this is we have a huge amount of data now from many, many different missions, which I'll talk a bit about Solar Orbiter. But how do we actually interpret this data and make the most out of that data to really answer some of those questions? And that is kind of the key to what I've been working on over the past few years.
Fantastic. And you've opened the story about science. A lot of people think that science is about finding clever answers, but you're just demonstrating here that it's more important to come up with questions about what's going on and coming up with a variety of questions that you can investigate. That's fantastic. Thanks, Laura. Now, we could do a quick solar physics primer for our listeners now. Could you just give us a brief outline of what are solar flares and what are, you mentioned, coronal mass ejections? What are they, Laura?
Yeah, absolutely. Right. So the sun's atmosphere, sometimes we think of the sun, we think of a yellow ball in the sky, right? And that's looking at the surface, what we call the surface of the sun, the photosphere. But when we look in the atmosphere of the sun, called the chromosphere, the corona, and if you look at the atmosphere of the sun with extreme ultraviolet wavelengths, for example, these are really kind of high energy wavelengths, we'll see it's really quite complicated. And you will see that it's a real magnetized environment, a lot of magnetic loops. And the sun is basically a ball of plasma. So it's rotating at kind of different speeds, different parts of the sun. And basically, what this ends up doing is it basically tangles the sun's magnetic field into this big spaghetti ball. If you want a better word for it, I don't know. But basically, this stores up all this energy in these kind of magnetic loops on the sun. And what happens every so often then is that stored magnetic energy can basically snap, like an elastic band snapping. And this can release a huge amount of energy. So a solar flare is basically like the outcome of this release of energy. So a solar flare specifically is a burst of electromagnetic radiation caused by magnetic reconnections. This is this breaking of magnetic field lines, if you like, that releases this energy. So it's a big burst of light where we see emission, so radiation from radio through to extreme ultraviolet, through to X-ray, and even sometimes gamma rays in extreme cases. So a huge burst of radiation. It is fast, intense, and as it's light, it travels at the speed of light. And these are huge amount of energy. We're talking about, billions of atomic bombs energy. So that's the light that we see, these bursts of energy on a very localized portion of the sun. Now, a coronal mass ejection is often accompanied by a solar flare, and this is actually a huge blob of plasma magnetic field that hurls away from the sun into space. So if you think of a solar flare as the burst of light, and then a coronal mass ejection or a CME is an ejection of material out into space. The CMEs are slower, right? Because it's not light, it's actually material. So these it's still fast in a sense, it's hundreds and thousands of kilometers a second. And they carry a huge amount of mass, and these are what actually cause very large geomagnetic storm and the aurora. So basically, if you think about it, flares are like the flash and CMEs are like the punch, right? So this is kind of how we think about it. And to give you kind of context, the sun has an 11-year cycle where it goes through periods of quiet time where there's not many solar flares and a period of max time, where we are currently now, where there's lots of solar flares. And we classify solar flares based on the intense X-ray emission that we see. So X-class solar flares are the largest flares. These are the ones that would definitely drive aurora, or M-class solar flares are the ones below it. And to give context of how often these occur, in every 11 years, there might be 50 to 60 X-class solar flares. So they're not regularly occurrent, but they're like transient large storm events. So that's kind of a context, a primer, if you like, for what solar flares and coronal mass ejections are.
Thank you so much. Your students must be so lucky to have you explain that with such clarity and enthusiasm. Thank you, Laura. Does sound quite deadly stuff, and we might talk about the danger a bit later. But let's have a little closer at solar flares first. Let's say a big solar flare bursts out from the sun in our direction. It's traveling at the speed of light, and it's going to hit us 8 minutes later. What happens? What is the effect on orbiting satellites? What's the effect on the ionosphere? Will there be any impact down here at ground level? What's going on?
Yeah, absolutely. So I guess the first thing is that as humans, we're grand. We have a lovely atmosphere and ionosphere that protect us from the ground level event, right? So we're never going to be impacted directly as humans, our physical bodies, by a solar flare. But where it does have a very dramatic impact is the ionosphere, and this is the ionized portion of the Earth's atmosphere. It's actually created by the sun, so radiation from just the general sun creates the ionosphere in our atmosphere. But when we have a solar flare, what happens is, as I said, a solar flare, a big burst of radiation from the sun, specifically looking at X-ray emission, which really increases by orders of magnitude when we have a solar flare. This basically penetrates down to the lower layers of the Earth's ionosphere and basically enhances it. And what this can do is it can disrupt radio communication. So we use radio communications that travel through the ionosphere, they bounce off the ionosphere, that lets them kind of travel around the world. So if you imagine then a radio signal traveling into that ionosphere, it's going to be impacted. So we can have high frequency radio blackouts. Um, it can disrupt GPS satellites, which if you think of a signal has to travel through that atmosphere to a satellite. So of course that is going to be disrupted. It can also actually impact atmospheric drag on orbiting satellites. So this is a big thing, is if you have a big storm, again, it's enhancing this ionosphere for which that satellites are traveling through at high altitudes. They can have atmospheric drag. So a lot of times, in some cases, satellites need to be pushed up a little bit. Um, so I guess the ionosphere reacts immediately to a solar flare. It expands, it can change GPS accuracy, affect high frequency radio communication, and even aviation routes. So if you think of going over polar flights, it might be kind of impacted by that. But on the ground, we really rarely notice that flares exist. It's not really kind of impacting us because we have this protecting ionosphere. Similarly, during a solar flare can also accelerate charged particles, and these are particles rather than light, but these can travel very close to the speed of light, and these can also impact satellites. So you can get single event upsets in electronics on board satellites and things like that. And if you think about a solar flare, although it takes 8 minutes to get here, most of our satellites that are observing the sun are basically at Earth, right? The furthest away, they're not that far away, they're orbiting Earth. So almost as we see it, it's already happened. And this is why we're going to predict them, I guess, right? Because we can't really forecast something that's only 8 minutes away. So yeah, that's kind of the impact of a solar flare as it hits Earth.
Fantastic. Whew. But what about CMEs, coronal mass ejections? They sound nasty. You described them as a punch before, but the same questions. What is a CME? How fast do CMEs move? And what happens when a big one hits us?
Yeah, absolutely. So a CME is really the thing that impacts our geomagnetic environment, right? These are the things that cause the aurora that have the most dramatic impact from a technological point of view and a space weather point of view. Now, a CME is usually associated with solar flare. If you have a large solar flare, it's almost 100% going to have a coronal mass ejection. And this again is if you think of explosion, this is the stuff that kind of is exploded out of the sun. So this is actually solar atmosphere material of plasma magnetic field that is hurtled away from the sun. And if it is, as we look at the sun, if it happens at the center of the sun, we know it's coming towards us, right? So a lot of CMEs, they go off the sun, we see them beautifully, but they're not coming anywhere near us. They might be hitting Venus or Mars or just going into interplanetary space. But a CME can take 1 to 3 days to arrive, right? Because it's traveling slower than the speed of light. And, one of the things we also want to be able to predict is when can we forecast they're actually going to arrive? But sometimes we usually have a bit more forecasting because we see a flare and then we say, okay, we've seen a flare, we know the CME is coming in a few days. Now, in terms of how that impacts Earth, when it hits the Earth's magnetic field, so again, luckily as humans, we have a magnetic field that protects us from these things that are blowing by. That's when real the party starts, right? So this is when you have this magnetic field and plasma that interacts with our own magnetic field, has a similar process of magnetic reconnection with our own magnetic field and that coronal mass ejection. And this is what can cause the aurora at the poles. So if you think the magnetic field lines of the Earth like a dipole, this is where kind of particles can trickle into our basically our poles. It gives us them a funnel in, causes the aurora both in the north and south poles, the northern and southern lights. This is a beautiful aspect. This is actually particles, whether it be in our own magnetic environment or from the sun that actually are traveling down those poles and interacting with our own atmosphere to cause the blue and the red colors, right? Basically, these particles interacting with, nitrogen and oxygen in our own atmosphere. And that's a beautiful side of it. But of course, then there are other things that can happen because of this geomagnetic storm. It really disturbs the magnetic field of the Earth. And this, in a sense, can have other impacts, such as affecting our power grids. So it can induce currents in our ionosphere. And this inducing currents can then induce currents in the ground. It can induce currents in our power grids. So what you don't want is more power flowing through your power grids, which can affect transformers. It can also have issues on pipelines. It can have issues again on GPS satellites. It can have issues, of course, on astronauts in space. It can have issues with a multitude of things, including satellite drag. So again, it disturbs the ionosphere. You have satellite drag. This is something you want to think about. Again, polar flights are something that we need to consider. So you do not want to be flying a polar flight when you have, if you think of the poles again, intense radiation coming through those poles. So the biggest geomagnetic storms come from the CMEs, or even multiple CMEs that interact with each other. So from a space weather perspective, these is the kind of doomsday thing. This is the CMEs are something that we really want to understand because they can have the biggest, I guess, technological impact on our technological stuff that we have here. And to give you some context there, Brendan, of what I mean by it's very easy to say hand wavy of these things cause bad things for our technological infrastructure. Lloyd's of London, which is an insurance company, actually earlier this year put out a report that the price of a very extreme solar storm would be over $2.4 trillion to the global economy, right? So we're not talking about, oh, we have a satellite down or we have a GPS issue. This is huge money we're talking about if this is the big question, we have an extremely large event on the sun.
Odds are it will happen one day. Thank you, Laura.
Yeah.
So you mentioned the European Space Agency Solar Orbiter community that you're a part of. Can you tell us a bit about that actual observatory? It's a beautiful spacecraft. What instruments are on board it? Where is it? And how do you get your data from it to do your research?
Yeah, absolutely. So Solar Orbiter is a European Space Agency mission in collaboration with NASA, and its uniqueness is that it's orbiting closer to the sun than Mercury. So it has this really unique orbit. It kind of has like an ellipsoid orbit where it goes inside the orbit of Mercury twice a year. And it also goes around the backside of the sun. So it's kind of orbiting the sun very, very different to Earth, which is really unique because most satellites that look at the sun are actually orbiting the Earth. So we only have one perspective. Now it's unique in that way of its orbit, but it's also unique in another way that it carries a whole suite of instruments, 10 instruments, and this combines remote sensing instruments. So remote sensing means it's taking an image, it's remotely sensing something. So it's taking an image of the sun and X-ray and extreme ultraviolet and white light observations of the sun with telescopes on board. But it also carries several instruments which measure conditions of the heliosphere or the magnetic environment at the spacecraft itself. So at the spacecraft where Solar Orbiter, wherever it is, it's measuring the magnetic field strength, it's measuring the speed of the solar wind, it's measuring energetic particles. So the key thing about Solar Orbiter is that it's combining remote sensing instruments so it can see what's happening at the sun and then measure what's happening as, say, coronal mass ejection passes it in situ. And then it also has this very unique orbit. So we're getting the closest ever images of the sun to date. And then also it's giving us this different perspective. So we're getting almost a stereoscopic view of the sun if we combine observations with Solar Orbiter with observations at Earth. So what I kind of mainly work on, I mainly work on remote sensing instruments, so taking images of the sun specifically with X-rays. So I look at flares, I love X-rays, high energy from the sun with an instrument called STIX. And I also look at extreme ultraviolet wavelengths. This is looking at high energy images of the sun with the telescope EUI. And we're getting some of the incredibly high cadence, high resolution images of solar flares, showing structure that we've never seen before. And going back to your point of new discoveries are just opening more questions rather than answering old ones, which is, I mean, this is part of science, I guess. And how the data is sent back, some of the challenges, I guess, with working with a mission with Solar Orbiter is telemetry, right? It's hard to get data back. We can't have huge data volumes because we literally just can't transfer the data from the satellite back because it goes very far away. It spends several months on the backside of the sun. We actually lose contact with it for like a week or two when it actually transverses the backside of the sun. So the data is sent back to like ESA ground stations, and then we analyze that data with open tools. But sometimes the data can sit on board for a month or two before we get it down. So it's not really, it's a science mission. It's not meant for doing forecasts, so we don't get real-time data, but we get kind of like we do campaigns of looking at high resolution observations of the sun, and we get those chunks of data back that we can analyze and answer some of those questions that I talked about.
Sounds like a perfect instrument. Fantastic. Wow. And what a clever orbit. That reminds
Mhm.
me, there have been quite a number of solar observatories over the years, starting with the wonderful Nancy Roman observatories launched over 60 years ago. Then we've had SOHO, Stereo, the Parker Solar Probe, that's zipping along there, to mention just a few. Is your ESA NASA Solar Orbiter, is it the best and brightest at the moment? And are there other solar observatories in the pipeline for future development?
Yeah, absolutely. Again, working in solar physics, we've had a rich heritage of observatories that have flown and are still flying to date. I mean, maybe I'm a little bit biased, but I would say that ESA Solar Orbiter is the best and brightest at the moment. I think it's giving us a whole new perspective of looking at the sun. And I think even though it was launched in 2020 and its science mission phase started in 2021, it's really only now that we're really kind of really gaining some new insights from that data. And I think that's only going to increase as we move into the next few years. I think as well as Solar Orbiter being this really exciting new mission, we're currently also in a golden age of solar physics and heliophysics research. Like the missions you mentioned there, SOHO, it's 30 years old last week, which is crazy and still working. So it's this combination of working with SOHO and Stereo. Stereo A is still working, and of course NASA's Parker Solar Probe. It's not just using Solar Orbiter by itself, but it's using it in combination with these instruments that is really giving us this multi-viewpoint, multi-wavelength perspective of the sun. And I think this is a really exciting time. I think it's almost a once in a generation time in solar physics that we have all these missions looking at the sun from a very different perspective, and also ground-based observatories. We have radio telescopes on the ground and white light telescopes like DKIST in Hawaii looking at the sun, that we really have this amazing viewpoint of the sun, and using these missions in combination is really what's making it very exciting at the moment. And thinking to the future, there are some other solar observatories in the pipeline at the moment. The situation in the US and some European funding cuts, it sometimes can be a bit worrying in the future of thinking what future missions there are. However, there are some, and we're planning some more. One is the Vigil mission. This is a European Space Agency mission. It's actually going to be a space weather mission, so an operational space weather mission. And the uniqueness of this is going to be launched in, hopefully by 2031 or 2032. This will kind of park at the Lagrange point 5. So basically, it will be out in space, not looking at the same position on Earth, but it may be 60 degrees offset from Earth looking at the sun.
Thanks, Laura. Now, I just did a search for your papers on the archive server and found you've worked on over a dozen different solar projects during this year alone. And we know very well that science doesn't always sail smoothly. And we're really happy to put our propeller heads on for a short time. The clarity of your explanations of solar research is just beautiful. Could you share with us some details of a particular part of your research now that you're working on that is driving you crazy, or is astonishingly exciting and beautiful? Or perhaps it's even both. What's going on?
Yeah, absolutely. And maybe, as you say, it's something that's driving me crazy, but it's also astonishingly exciting is, as I said, with Solar Orbiter, we're taking the closest ever images of the sun to date, and we ran a series of flare-focused campaigns. So Solar Orbiter doesn't always look for flares, it looks for other things in the sun, but we ran some campaigns where we pointed at an active region, part of the sun that was most likely to flare, with our high-resolution telescopes, and we wanted to see these things called flare ribbons, which are basically parts of the solar atmosphere where most of the energy of the flare is deposited. We wanted to see this with extreme resolution. So we looked at these flare ribbons, And with the fastest timescales we've ever had, so we looked at them at 2 second sampling. So every 2 seconds we have an image. So before that, we only had, 10 or 20-second sampling, and also with much better spatial resolution. So we were trying to see the deposition of energy following a flare into the solar atmosphere that then produces all this radiation. And we're actually starting to see is that these flare ribbons evolve on timescales much shorter than we actually had thought. They actually change very, very quickly, and they're much, much smaller than we thought. And what we're seeing is these tiny kernels flashing on and off within flare ribbons. So it's almost like the flare is made up of all these tiny little explosions. And we're trying to understand that in the context of I guess, our standard model of a solar flare, because usually when we look at X-rays, this is how much, how many accelerated electrons we see following this energy release. We see where that's deposited in the solar atmosphere. But now we're seeing that that area in which it's deposited is much smaller. So the power in those accelerated electrons is much, much higher. And why that's also driving me crazy is like, how do we understand that in the context of our standard flare model and our physical models that we use to drive solar atmospheric response and emission? But then it's also exciting because it's telling us some new science. And it goes back to this idea of we're seeing smaller and smaller things. And the question is, if we had higher and higher in resolution, do they get smaller and smaller and more intricate? And I guess this is something that's really exciting because it's opening more questions about flare energy release and deposition. But it's also driving me crazy of how do we interpret this data? And specifically also, how do we combine this images of these high resolution with extreme ultraviolet light with our X-ray images? So we make X-ray images very differently. Kind of works like a strange radio telescope on board that we basically construct an X-ray images from four components of these profiles that we get down from X-ray. So how do we combine that together? So the thing that's driving me crazy is working with the data and making the most out of it. But it's astonishingly exciting to try to interpret this data for new things. So that's kind of something that I've been working on and will continue to work on for the next year at least, is trying to understand this data in the new context.
Fantastic. You heard it here. Laura and her colleagues are taking X-rays of a sun and putting that huge sun under the microscope. Okay. Look, just to follow up on that, as a solar physicist, you're immersed in solving some of, as you've just demonstrated, the most complex and puzzling phenomena in our universe. Now, for example, that inexplicable temperature gradient that our sun has. Could you introduce our listeners to that particular puzzle, and are we going to solve that puzzle soon?
Yeah, absolutely. So this is known as the coronal heating problem. And what this means is that the corona is the atmosphere of the sun, and the surface of the sun, the photosphere, its temperature is around 5,500 degrees, right? So still that's extremely hot. But when we move away from the surface of the sun and we move into the solar atmosphere and we move further away, the corona is over 1,000,000 degrees. So it's basically like you're walking away from a fire and it starts to get hotter. And the reason it's a problem is that we don't understand why that is yet. We don't understand what energy or what conversion of energy is going to heat the solar atmosphere. And in terms of trying to interpret that, there are kind of two main theories. One is that you have small scale waves that are continuously propagating energy away from the surface of the sun into the solar atmosphere and depositing energy there that's heating the corona. Or we have nanoflares, so really, really small flares and small reconnection events that are contributing to this heating. And they're just so small that we can't see them yet with our current resolution, but they're there. There's a scaling between small and large flares, and maybe this continuous energy release is heating the solar corona. And we still don't have the answer yet. We still don't know whether it's one or the other. It can, of course, be a combination of both. And I think in terms of, are we going to answer that question soon? I think we're getting there. I think one of the frustrating things about this, I don't think it's going to be oh wow, now we've solved it. This is the solution. It's probably going to be a combination of both. And I think instruments or missions like Solar Orbiter with the high resolution observations are really helping us to kind of test these long-standing theories of the contribution of waves versus small flares to answer that. But we're getting there. I think, maybe in the next 20 years following this golden age of solar physics, we might be able to answer that long-standing question.
Beautiful. Small steps. Excellent. Thank you. Now, can I bring up one last puzzle, please, Laura? And I alluded to this earlier. I found one of your first author papers from 4 years ago that you wrote right in the middle of COVID, and we're not going to talk about that yet. You found out something amazing about that brightest object of all time, affectionately known as a boat, a gamma ray burst, or GRB, from 2 billion light years far, far away in another galaxy that blasted into Earth's atmosphere and messed up our ionosphere. Now, the question is, what happens if a GRB hits us from within our own galaxy? Is my tinfoil hat going to work?
This is a great question. So this was a nice kind of side project almost I did where we have an ionospheric monitor in a field in Ireland, and we use it to basically measure flare impacts on the ionosphere, right? So when the X-rays and gamma rays from the sun impact our ionosphere, we can measure the ionospheric disturbance. And when this boat happened, I was like, I wonder, could we detect it in our ionosphere? And we did, and we actually saw that this boat, which was, as you say, 2 billion light years away, actually ionized the upper atmosphere, which is really quite crazy. Um, so the question is, that happened, what, 2 billion light years away, really far away. What would happen if that happened in our own galaxy? That caused a solar flare impact of something so far away. But the good thing is that these events are extremely rare, and the chances of one happening in our own galaxy are basically non-existent in our lifetime. But what would happen is more that you would have a really dramatic impact on our atmosphere, right? It would deplete the ozone layer. So UV rays then from the sun would have a dramatic impact on life on Earth. It would impact, our climate. It would, and things like this that would be disrupted for many years. So it's not that, these kind of doomsday science fiction that a gamma ray burst will happen and our whole world will explode. It won't be like that. It will just have a really dramatic impact on our ionosphere. And then we would have to start worrying about things like the sun because we wouldn't have the nice protection of our own solar atmosphere. Um, but again, these events are extremely rare and usually not pointed anywhere near us. This boat was, amazing that it happened that far away, but it was exactly beamed at Earth that we were able to detect it. So I think we're okay. We don't need any tinfoil hats as of yet. Yes, if it happened within our own galaxy, we'd have bigger problems that we need to worry about for sure.
Excellent. So probability is on our side. That's good to know. Thanks, Laura. Now, as a solar physicist, you're on a quest to solve these complex mysteries of our sun. How do you do your best thinking? What circumstances do you usually need to swim through that huge sea of data and come up with verifiable conclusions and new understandings? What situations and surroundings do you prefer, Laura, to support your best thinking?
Yeah, this is a great question, right? Because a lot of the time, when you're doing research, my type of research where I'm looking at observational data, I'm basically hunched over my computer to look at it, right? And sometimes when you get so deep into it, it's hard to see the wood from the trees and you need perspective. And I think from my thing, some of the best ways I've got my best thinking is actually being away from a computer screen, whether it be, cycling, I cycle in and out to work. And this is a lot of the times I usually on my cycle home where I have a bit of perspective and I'm kind of half thinking about it, that something comes out. I think talking with colleagues for me is essential. I get my best science done in a collaborative environment where I have a colleague comes to visit me or I go to visit them or we're at a conference or we're in the pub after the conference talking about science away from the computer with a different perspective. I think that's kind of the key things for doing research. It's sometimes hard when you get so deep into the data, but taking a step back sometimes is really needed to really connect the dots, to solve those complex mysteries of the sun, as you say.
Fantastic. Getting some brain space. Thanks, Laura.
Yeah.
Now, what about your non-research work? Do you have any other responsibilities at the Dublin Institute of Advanced Studies? You're a professor there. You have teaching responsibilities?
So no, actually, it's interesting. So at the Dublin Institute for Advanced Studies, we are a research institute. So we do not necessarily have we don't run classes. We're basically 100% research. Now, in
Sure.
saying that, we do host master students and PhD students and undergraduate students, and we register them at universities. So we work with students a lot and we do some teaching, but we don't have any necessarily direct responsibilities to teaching, which is a really, I'm aware that's a really privileged place to be in terms of then giving your 100% of your time to research. But one of the things I do love doing is to teach and to supervise students. So I have some undergraduate students that are working on some projects, like a PhD student, and I do love teaching in that aspect of research and facilitating how you kind of go from learning what you've learned in your lecture to then actually putting it into practice. That is something that I really enjoy in terms of my non-research me over computer working on this. At DIAS, or the Dublin Institute for Advanced Studies, we actually work out in an old observatory called Dunsink, and we run visitor nights. So one of the big things that I am personally passionate about, and one of our responsibilities at DIAS, is to host visitor nights and outreach and engagement for the public, and to get people in to learn about the research that we do in Ireland and at DIAS and the history of research that we have here. So one of the things that I kind of do is work with giving talks to the public, to engaging with the public, or to help facilitate these visitor nights at our observatory.
Fantastic. Now, I've had a look at some of your published papers. There's a lot of them. And I noticed that you wrote a number of them when the COVID pandemic was at its peak back in 2020, 2021. How did COVID affect you and your family, and what was the impact on your solar research? Were there lessons learnt?
Yeah, absolutely. It was a very strange period. And going back to, earlier when we are talking about advice to early careers, I was living in the US at the time. I was working at NASA Goddard, and I had planned to stay there for several years. I had more money on my contract to continue working there. Um, but COVID happened in 2020. My now husband, my boyfriend at the time, basically flew back to Dublin to renew his visa in March of 2020 and ended up getting stuck here. So I lived in a basement apartment for a long time by myself, and maybe this is why I published a lot of papers. Um, but of course, it was a challenging time, and that basically the reason of the long distance and the challenges with the pandemic and being away from friends and family at the time, living in a basement by myself in DC, was really the reason of coming back to Europe. And at the time, I was really disappointed about that. I really didn't want to leave the US, but everything has worked out now. I wouldn't have got involved with Solar Orbiter or being back in Dublin now. So things do work out in the end. And I think, what did that teach me in terms of astrophysics research? It was great at the time when everyone was locked down and we could do Zoom and we could collaborate that way. But I think I learned about myself that I'm definitely more of a people person. I need to be around people. And this goes back to, where do you do your best research? Is talking to people in person and informally. And I think that has taught me that, having the opportunities to work with people in person is really important to me. And that, of course, was challenging. But we made it through. It's crazy to think now that it's almost 5 years ago that happened. But there were definitely lessons learned. I worked on lots of different interesting things at that time, which was great. And it gave the space, I guess, to think about different research. At the start, it was great. It was when it started to drag on, I think, as is all, it got to us eventually.
Excellent. The cloud with the silver lining. Thank you, Laura. Well, you've painted the big picture of solar physics. We've looked at your early research and we've looked at your very current work, and we've put our science hats on just for a little while. Would you like to tell us about some of the things outside your research that regularly bring you great joy?
Yeah, absolutely. So I guess, my job, as many of us, is sitting by a computer. So things that bring me joy is not being at a computer, it's being outside. And I moved back to Ireland around this time last year, and I'm really enjoying being able to go back out into kind of the wilderness, doing some hiking. I lived in the Netherlands before, and it's great, but it is incredibly flat. So it's nice to be back near some kind of mountains and be outside during the weekends to go hiking, and cycling is another thing I'm very passionate about. This might seem crazy to you, Brendan, because you're in Australia, but I do swim in the sea here in Ireland, even in the winter.
Oof.
And I think this cold sea swimming is something that really, at the time, maybe doesn't bring me great joy, but when you kind of get out of the sea again, it does. So that is something that, wild sea swimming is something that I also do when I can outside of my research that brings me joy. Yeah.
That sounds wild. I looked at the temperature in Dublin yesterday. It was 5 degrees there, and we had 35 today.
Wow. Yeah. Can't even imagine that now.
Quite a contrast. Okay. One of the things that comes with great joy is sort of looking forward to things. Now, Laura, are you, like me, perhaps a little disappointed when we get through another solar cycle maxima, like we just have done, without another Carrington event happening?
Yeah, I most certainly am, right? As a solar physicist, we always say like, oh, if the sun did a big bad explosion, it would be very bad for us all. But deep down, you really want to see one happen, right? You want a really big solar storm to have these dramatic impacts so that you can say, hey, look, wow. But also from a physics point of view, right? It's interesting to see these large events. We're always trying to see the big, bad, and ugly events that will happen. So a little bit disappointed that we haven't had a huge, massive solar storm this solar cycle that has really had a dramatic impact. We've had a few. Now, I will say that we're not over yet, right? We are currently just over the maxima. So we're on our declining phase now. But as we've seen of the last solar cycle and even the solar cycle before that, some of the biggest flares that happened actually happened in the very declining phase, almost as it went back to being at solar minimum. So, Brendan, I would say that we can be disappointed, but we can still be hopeful that maybe a big solar storm will still happen in this solar cycle.
Beautiful. There is always something to look forward to. That's fantastic, Laura. Thank you. Now, you mentioned outreach before. You've done heaps of it. I've seen some of your great videos that are online, and you share a lot of your resources on GitHub. I'll give a link to that at the end of this interview. Is outreach an important part of being an astrophysicist? Do you have anything in the outreach pipeline at the moment?
Yeah, absolutely. I think outreach and engagement is fundamental not just to astrophysics, but any scientific research. Our most of our work is publicly funded, and it's really important, I guess, to get the community interested in it, and sharing that knowledge is something that I think personally is very important. I guess another reason why I'm passionate about it myself is that I think growing up I didn't, as I said, I didn't even know we did astrophysics research in Ireland. I was just completely unaware. And I think, if I'd known back then, I would have even been more excited. So it's showing, I guess, the younger generation or to kids that there are possibilities and we're doing research in Ireland or in the world, which I think is really, really important. And I really do enjoy giving talks. Sometimes when I'm having a bad research time, when I do a visitor night, I'm like, oh, this is why I'm doing it. Oh, it's amazing. I get to do research. This is so cool. It gives you perspective. Absolutely. So I think it's hugely important. And it's also, to be fair, when you study the sun, it's actually quite easy to do engagement because we have these beautiful movies of the sun. We have beautiful observations. So it's easy to actually genuinely show the data that we're working on and just to give a context of looking at our closest star, which I think is amazing that we have that opportunity to do that. And people are generally interested in astrophysics, this curiosity of where we are in the universe. Um, I think anything else in the pipeline, I have kind of a few ideas I'd love to do next year. One of the things that we'll definitely be focusing on in DIAS is that we have a partial solar eclipse next year. In Ireland, it'll be around 98% totality. So this kind of gives us an opportunity to again bring people in. People are interested in the solar eclipse. Why are we interested in the solar eclipse? What can it tell us about the solar atmosphere? So I think there will be a lot of eclipse related outreach and engagement next year, which will then kind of hook into our solar physics research that we do at DIAS.
Excellent. Fantastic. That sounds great. And also, it's a great time now, I reckon, to recruit young astrophysicists because I think there's a burgeoning interest in auroras at the moment. And when people look up at an aurora, I'm sure there's a lot of people saying, wow, that's beautiful. I wonder why it's happening. So let's hope this solar maximum, as we go down the other side of it, we get a few more astrophysicists that want to study the sun and its auroral effects. Thank you very much, Laura. Look, we're rapidly running out of time, but I've certainly got plenty of time here to hand you the microphone and tell you that it's all yours. And you've got the opportunity to give us your favourite rant or rave about one of the challenges that we face in science, in equity, in representations of diversity, or science denialism, that's my bugbear, or science career paths, you've alluded to them earlier, or your own passion for research, or that huge human quest for new knowledge. The microphone, Laura, is all yours.
Oh, well, thanks, Brendan. I mean, each thing you talked about there, I could probably continue on for another 2 hours. But I guess I think a key thing is at the moment it's particularly challenging with scientific funding is career paths in academia, right? It's very challenging to be an early career researcher in many ways, to having the support systems for doing 1 or 2 year contracts around the world that aren't paid that very well, you know, to making it a more accessible place, I think is really important to kind of help thrive, to kind of the younger generation to come in and to find permanent jobs. Like that is the health of scientific researchers, having good researchers there. And I think we do lose an awful lot of researchers every year. Like I know myself, like I was almost gone a few times, and a lot of the time it's luck of the draw, right? You can do everything right, but if you're not in the right place at the right time with the right opportunity, you're lost. You might leave and then you don't come back. And it's not, I don't think it's a thing of when you leave, you can't come back. I think when people leave, they don't come back because it is hard to get back in. And if you look at, say, the long working hours or the kind of limited funding or this, a lot of it is you don't have the stability or you don't know where your next contract is going to come in a few months. And this can really wear on you. And this occupies a lot of your time when you should be putting it into fundamental research. So I think one of the things I would like to see is the whole academic system needs to change in terms of its funding systems, in terms of how we support people to actually contribute to a career in research. And this is important to making sure it's diverse, making sure we have all voices available there, because I think that really makes good research happen. So we do all this amazing research, but the reality is when you talk to the scientists, especially early career scientists, are burnt out from this thoughts of instability for not knowing where the next grant is coming from. So I would love to see over the next few years the academic system kind of change and to make sure we don't lose brilliant scientists we lose their representation. Talent is everywhere, but opportunity isn't. So if we can think of ways to fix that, that would be something I think is really important for research going forward.
Excellent. And that's a job for everyone. Thank you. Now, Laura, is there anything else we should watch out for in the near future? What are you keeping your eye on?
Yeah, this is a great question. I mean, obviously, maybe again, I'm biased, but I think I'm looking at the new science discoveries we're going to see in heliophysics and solar physics research over the next few years. Going back to this idea of living in a golden age of solar physics, we have missions like Solar Orbiter, we have Parker Solar Probe, we have a whole suite of ground and space-based instruments looking at the sun. I think we're going to really start to understand some of those open questions. So that's kind of what I'm going to be keeping my eye on of even data that we already have taken and we're sitting in databases, but really getting the most out of that. And this idea of, using AI in a correct way to interpret that data, right? I think we are living not just in research, but in the world of this AI kind of new thing coming online and what is it going to do? I don't think it's the be all and end all. I think it's an amazing tool. And if we use it correctly, we actually will be able to answer some of those scientific open questions, even with the data we have. So I'm very excited to see what will happen in the near future in that regard of this wealth of data that we have and how can we find new science discoveries from it.
Beautiful. Thank you, Laura. Okay, everything you've been saying has been so grand. Thank you so much, Dr. Laura Hayes, on behalf of all of our listeners, and especially from me. I learned so much by osmosis. It's been really exciting to be speaking with you way over there in the land of my ancestors. And thank you especially for your time. Good luck with all your next adventures and all your future travels. And listeners can tune in to Laura's research. They can find Laura on GitHub. And the easiest way is to go to tinyurl.com/Laura CME. That's all lowercase, Laura CME on tinyurl.com. So, look, Laura, I can't thank you enough. This has been fantastic. Thank you, Laura.
Thank you so much, Brendan. It's been lovely to chat and thank you for the opportunity.
Good night.
Good night. Take it easy. Bye bye.
And remember, Astrophys is free, no ads, and unsponsored. But we always recommend that you check out Dr. Ian Musgrave's Astroblogger website to find out what's up in the night sky. Keep looking up. Radio Wave!